Hello everyone, today I will be solving problem 5.32 from Introduction to Electrodynamics by Griffith. The problem states for part A, we have to check equation 5.76 for the configuration in example 5.9, and for part B, we have to check the equations 5.77 and 5.78 for the configuration in example 5.11. So, for example 5.9, we have a very long solenoid that consists of n closely wound turns per unit length on a cylinder of radius r, and each carries a current I. So basically we have found already that if we draw an Amperian loop, so if we draw an Amperian loop and it has a length of L, we can find the magnetic field outside and inside the solenoid. But first of all, let me write down what 5.76 really is. So we have, so to solve for this one, we can find, we already know that outside of a long solenoid, the B field is 0, just because it's a constant. And if the B field like at an infinite distance of the solenoid is 0, therefore we can assume that the B above the surface would be also equal to 0. So B above is 0. Okay, and we know that there's no magnetic field outside of the long solenoid. So if we take that the magnetic field is constant outside of the surface, then at a very far point like infinity, there won't be any magnetic field. Therefore, right above the surface, we can just assume that it's 0 as well. And to find the magnetic field below the surface, we can use, so what we'll have is that the magnetic field inside the solenoid will be constant, so we can pull that one out of the integral. And then, well, this will be B below. And if we integrate over the path, we will just be focusing on this, on that segment, since on these other perpendicular segments, they will not contribute. So there's only that segment that I put the rectangle around, and that length is just L. And that's equal to mu naught. And the right side of the equation, we have to multiply this current by the amount of turns that the solenoid has. So that is Ni. And so if we want to solve for the magnetic field below the surface, we would have, and this term right here, we can just call it big N. This is a very long solenoid and the turns are super closely wound, we can assume that the current around this solenoid is a uniform surface current. So we can replace this term by that surface current that I'm talking about. And this expression would be like this. And using the right hand rule, if we curl our fingers in the direction of the current, our B field would be pointing upwards in the z-hat direction. And then we can see that 5.76 is requiring us to cross our K, our surface current, with the vector, the normal, okay, the vector normal to the surface. And then in this case, we can see that it would be in the s-hat direction. So we can say that the right hand of the equation is mu naught. And then we see that if the current is going in that direction that we see on the picture, that means it's going in the circumferential direction, so phi. And phi hat cross s hat gives us negative z hat. Alright, so if we write down equation 5.76, we have that 0 minus our result, which is mu naught k z hat, and it equals the result we just got. And we can see that these do agree. Therefore, equation 5.76 does check for this configuration. Now we have to check equations 5.77 and 5.78 for a spherical shell. And what we have for 5.77, we'll be checking if the vector potential above the surface is equal to the vector potential below the surface across the boundary. And we are provided in the example, we are provided the vector potential. And to check that 5.77 works, we have to plug in our value of little r at the boundary, which would basically equal to big R. So when we plug it in, they should equal the same thing. So when we plug in big R on the left side, we are left with mu naught r squared omega sigma sine theta over 3. And then on the right side, the r to the fourth cancels with the r squared and leaves us with r squared at the top. So 5.77 does check. 5.78 states that the partial derivative of the vector potential above the surface with respect to the normal minus the partial derivative of the vector potential below the surface with respect to the normal is equal to negative mu naught times k. To start off, we can see that the normal direction in this configuration will be the r hat direction. So we will be taking our partial derivatives with respect to r. And to start off, let me just clarify first which one is above and below the surface to not get confused. And okay, first one, above the surface, we're only taking the derivative with respect to an r squared on the denominator. So let's first write out the constants. And now we can see that this r squared is, we can be rewritten as r to the negative 2. And when we take the derivative with respect to r of this, it just gives us negative 2 r to the negative 3, which is also negative 2 over r cubed. So that is what that partial derivative gives us. And we can't forget that it has to be evaluated at the boundary, okay? And now for the vector potential below the surface, we see there's only one r on top. And so everything else is constant when taking the derivative, so we just literally have that term without the little r. And again, technically has to be evaluated at the surface, but we don't have a little r, so we don't need to worry about that. So when plugging in r for the vector potential above, we're going to have -2, and then this big R cubed will cancel with the R to the fourth, and we're literally only left with -2 mu naught R omega sigma sine theta, and then that's in the phi hat direction, and let's not forget the over 3, and then this term stays the same. And then all we need to do is -2/3 minus 1/3, and it will give us just negative mu naught R omega sigma sine theta in the phi hat direction. So now we need to verify that this equals to negative mu naught times the current density K. And the current density K is the surface charge, so this one will be equal to sigma times the velocity vector. The velocity can be rewritten in terms of its angular velocity, so we will just have sigma times omega vector times the r vector. And this cross product is the product of the two magnitudes times the sine of the angle between them, which in this configuration is going to be theta. And the direction will be phi hat, just because omega is pointing in the z hat direction, r is pointing in the r, so that just leaves us with sigma omega r sine theta phi hat direction. And now if we multiply this by negative mu naught, this gives us negative mu naught sigma omega r sine theta phi hat, which just happens to agree with our first result. So we have checked that 5.77 and 5.78 work for this configuration. Thank you.